Good morning, good afternoon, good evening. We're going to talk about Avogadro's law. So again, you have a simple gas law that will be illustrated here, one you've seen in your lab that you did last week. So Avogadro deals with volume versus number of moles. That ratio is always constant for a gas. That is, of course, if temperature and pressure are constant. So we're only dealing with two variables at a time right now. So volume over number of moles, constant ratio. And since we have a constant ratio, that means that if we increase the volume by a factor of 2, for example, the number of moles will also double. Or if we triple the volume, the number of moles will also triple. So that ratio here remains constant, which allows us to use this equation here, V1 over N1 is equal to V2 over N2. So because we have this type of fraction, that gives us a linear function. And you can see that that linear function ends up at the origin. Why? Well, if I have no matter, so no mole of anything, well, no matter can't have a volume, right? So 0 mole would correspond to no volume or 0 volume, which is shown here by the line touching the origin. Okay, I will skip the whole mole concept, which you should know about. So I will skip the slide here. If you have questions, you can always ask me in class, but since you did the review at the beginning of the book, you should have no problem with this. But again, if you're still uncertain about conversions from mass to moles or stoichiometry itself, just see me in class and I'll review that with you. So let's now see how the kinetic theory applies to this gas law. So we have a container here, and the lid can move back and forth based on the amount of pressure applied on it. So we have a given amount of gas particles, and those gas particles are, moving and colliding, and it's all nice and good. Now, what would happen if I increase the number of particles in the same volume? Well, suddenly there are more particles, which means there will be more collisions, right? So in order to keep the pressure constant, the only way is actually for the lid to go up, so you see it here, which means you now have a bigger volume. So again, more particles mean more collision, which would imply that there's more pressure if the volume stayed the same. But in this case, we're trying to keep the pressure constant, so the only way to keep that pressure constant is by going to a bigger volume, and therefore we're reducing again the amount of collisions in spite of the fact that we have more particles inside the container. So more particles, more collisions, but we don't want more collisions, so the only way to alleviate that is to create a bigger container to keep the number of collisions constant and therefore the pressure constant. Now the reverse would also be true. If I remove certain particles, then there would be less collisions, and we don't want that. We're trying to keep the pressure constant. So in order to keep the same amount of collisions, if I remove some of the particles, well, if I want to keep that amount of collisions constant, I have to take the lid down to a certain degree to allow the amount of collisions to remain the same. Okay, so that's how it works for the kinetic theory. If you look at your textbook, you have a few mathematical examples of problems about Avogadro's law. So here's the first one. I highlighted for you in yellow the V1 and N1, and in green the V2, which we're looking for. And N2 actually is not 0.2. N2, if you read the question properly, it says, what will the new volume of the balloon be if 0.2 mole of helium is added to the balloon? So originally we had 15 liters, which contained 0.5 mole of helium. To that 0.5 mole, we add 0.2 mole. So they want to know what will be the new volume. Obviously, it won't be 15, so we have to calculate it, right? So the number of moles total at the end is 0.5 plus 0.2, which gives us 0.7, right? So we could, if we wanted to replace let's say green. So here we would have 0.7 mole, and originally we have 0.5 mole. We have an original volume of 15. We're looking for the final volume. So we just replace in this equation here, and we solve. It gives us 21 liters. Okay, here we have a second example. How many moles of gas are there in a container holding 69.2 liters of methane at STP? So again, I color-coded everything. So how many moles? N of gas are there in a container holding 69.2 liters, that's my V, at STP. Now we know that at STP, the volume is 22.4 liters for 1 mole. I showed you that in the previous lesson. So those parameters you'll have to learn. They may be given to you on a test, but it's better if you know them by heart just in case. The pressure, the temperature, the number of mole, and the volume at STP and at SATP. So at STP, 22.4 liters for 1 mole. So all we need to do is do the ratio. Again, you're using that famous equation, V1 over N1 is equal to V2 over N2. So here they replace the volume. I'll use the same colors. So the volume at SATP, the volume at STP, the number of moles at STP, and on the other side we have the volume at the final volume, and we're looking for the number of moles that corresponds to this volume. So all you're doing is a ratio, and your answer is 3.10 mole. Now here, if you notice, they say it's 1 mole at STP. If you look at the significant figures, that kind of messes up this here. They made a mistake. They should have put 1.00 in order to get this, and that's why in the chart that I put in the previous lesson, I did put 1.00 this way. It does not penalize you significant figure wise. Okay, so here there's a little mistake at that level. Again, here's another example. Propane, C3H8, which by the way is a hydrocarbon, right? Because we have carbon and hydrogen together in the same compound. So propane burns in the air according to the following equation, which you have here. What volume of oxygen, so what volume of oxygen, so both in green, is needed for the combustion of 35.0 liter of propane if the volumes are measured at the same conditions of temperature and pressure. So again, I put the volume of the other substances in yellow, and the substance in the equation is also in yellow. And you're going to say, but miss, why are you doing that? Who cares about the equation? Well, in this case, they're only giving you volumes, right? They're not giving you numbers of moles. But your equation provides you with some information. You know that the ratio of propane to oxygen in this combustion is 1:5. So you can use that as your number of moles because your volumes will keep the exact same ratio. So you have it here, 1 mole of propane, 5 moles of oxygen. If I work with 35 liters of propane, what volume of oxygen do I need? So you have basically V over N is equal to V over N. Yes, it looks like it's the reverse, N over V, but in the end, with an equation like that, it doesn't really matter. You could very well put N1 over V1 is equal to N2 over V2. It would do the same trick, right? So all you have to do is cross multiply like this and like this, and we find our answer, which is 175 liters. So 5 times 35 divided by 1 gives me 175 liters. That's the amount that I need, the amount of oxygen. So there is a part B to this question, and it says, what volume of carbon dioxide will be produced if 155 grams of propane react with enough oxygen at SATP? So we're looking for volume of carbon dioxide, but we're given a mass of propane. So the first thing you'll need to do, if you go to part B, is to convert that mass of propane into an amount of moles. So molar mass of propane is 44 grams per mole. So it gives us 3.52 moles. Now, according to our equation, 1 mole of propane will produce 3 moles of carbon dioxide. But now in this case, we're not working with 1 mole. We calculated that we have 3.52 mole of propane in this exercise. So we're going to do a ratio. I put it here because I don't like the way they solve it in just one step. It's not very clear. So if I have 1 mole of propane for 3 moles according to my equation, if I was to work with 3.52 mole instead of propane, how many moles of carbon dioxide would I release? I would release 10.56 mole of carbon dioxide. Now, knowing this, they said that all this is happening at SATP. So what is the volume occupied by this amount of carbon dioxide? Let's verify. At SATP, the volume is 24.8 liters for 1 mole. If I have 10.56 mole, what volume of carbon dioxide does that occupy? I again just do my ratio, and I get an answer of 258.7 liters. Now I want to point out 2 things to you. First of all, I just put 1 mole here because I don't have enough space to really write more, but I should have put 1.00 moles, so that way I would have not been limited with my significant figures. Secondly, their significant figures here are wrong, but it's not that they're wrong, but in their final answer, they do give you the right amount. So 259 liters, 3 significant figures. So that is fine. One thing I want to point out to you is that they use here 24.5 liters as an SATP value. So I just want to put it here. So 24.5 liters for the volume at SATP. And you will see that from textbook to textbook, or even if you go online, strangely, they don't seem to agree on this volume and sometimes on the pressure at STP. It'll be slightly different than what I showed you in the previous lesson. It doesn't really matter, just work with what you're given. If you're not given anything, work with what I gave you in the previous lesson. Or on a test, if you have some kind of memory aid provided, work with the values that are given to you. So as long as you know how to work with those values, regardless of the actual values, you're going to be fine. Okay? Next, I have practice problems for you. So as usual, if you want, you can always read the problem, do it by yourself, pause it in the meantime, and then look at the solution. So here we have, predict the volume of oxygen required for the complete combustion of 120 ml of butane from a lighter. The oxygen and butane are measured at the same temperature and pressure. So I'll cheat a little bit. I'll skip to the next slide, which is a kind of mirror image. So predict the volume. I'll highlight just to help you out. Volume of oxygen required to complete the combustion of 120 ml of butane from a lighter, right? We'll need to use, in this case, because we're not provided with any information regarding the moles, we'll have to use the ratios from the equation. So 2 moles of butane for 13 moles of oxygen. So we're looking for the volume of oxygen. The equation says 13 moles are required if I'm using 2 moles of butane, and I'm given a volume of 120 milliliters of butane. So again, I will do my ratio, which is just a cross multiplication, and the answer is 780 milliliters. Finally, you have one last practice problem. So it says a gas system has an initial volume of 9,660 milliliters with a number of moles unknown. When the volume changes to 7.78 liters under conditions of constant pressure and temperature, the number of moles is found to be 0.0816 moles. What was the initial number of moles? So again, I'll cheat. I'll skip to the next one. I'll just highlight a few things for you to help you out. So we have an initial volume of this, number of moles unknown, and the volume changes to this, and this is the amount of moles. I just realized here I made a little mistake, so we're going to have to convert this. Your volume here is in milliliters, this one is in liters, right? So I got caught, which probably you would do too. So this changes to liters, and this would be, if I convert the same thing into liters, because I need to have the same units, it would be 9.0 0.060 liters. And my number of moles related to the 7.78 is 0.0816, so I have it here. So then I just need to, again, do a ratio or cross multiply. 0.0816 times 9.06 divided by 7.78 will give me this here, 0.0950 mole. And actually, there shouldn't be a 0 here either. Oh yes, there should be, sorry. This is fine. We have 3 significant figures, 4 sig figs. We're allowed to keep 3, so 950, that corresponds to 30. So let me just erase, oops, not let me erase this. So that is fine as an answer. Okay, that's it for today. So stay tuned for your next simple gas law episode. Ciao.